Okay, let's start the class. So today our topic is S block elements. Okay, and today I shall discuss physical and general properties of alkali metals. Okay, so alkali metals belongs to group 1A. Okay, so in group 1A, these are the elements present, that is hydrogen, lithium, sodium, potassium, rubidium, cesium and francium. Okay, so what is the atomic number of this element? Hydrogen 1, lithium 3, sodium 11, potassium 19, rubidium 37. Okay, rubidium 37. Next, cesium. Cesium atomic number is 55. Okay, and francium atomic number is 87. Okay, so these are the elements of group 1A. Okay, so the alkali metals refer to lithium to cesium. Okay, lithium to cesium, we discussed the properties of lithium, sodium, potassium, rubidium and cesium mainly, okay, in this class. Okay, so first we discuss the general characteristics of alkali metals. First we will discuss the general characteristics of alkali metals. Okay, so in general characteristics, the first point is electronic configurations. Okay, the first point is electronic configuration. Now if we take this table, okay, so these are the elements. Okay, hydrogen. Now in alkali metals we refer to lithium to cesium mainly, and also francium, but we not discuss the properties of francium. We only discuss the properties of lithium to cesium. Okay, but it also, the francium also includes in alkali metals, but not hydrogen. Okay, okay, so lithium, its electronic configuration is, the general electronic configuration of alkali metal is noble gas configuration, then NS1. Okay, so N is the principal quantum number. Okay, so for lithium it will be 1s2 2s1. Okay, 1s2 2s1. So 1s2 is the configuration of helium. Helium is noble gas. Okay, next sodium, 1s2 2s2 2p6 3s1. 1s2 2s2 2p6 3s1. Clear? Okay. Next, potassium. So 1s2, 2s2, 2p6. This is the electronic configuration of neon. Okay, neon. So this one is helium, noble gas, and this one for neon. Clear? Okay. Next, potassium. Okay, so potassium electronic configuration is 1s2, 2s2, 1s2, 2s2, 2p6. Okay, next 3s2, 3p6, 4s1. Okay, so 1s2, 2s2, 2p6, 3s2, 3p6. This is the electronic configuration of argon. Clear? Okay. So next, rubidium. Its atomic number is 37. Okay, so here we write the electronic configuration of rubidium. Okay, so 1s2, 2s2, 2p6, 3s2, 3p6. Next, which orbital comes? 3d. Okay, 3d. Okay, yes. So 3d comes 3d10. Okay, next 4s2, 4p6, 5s1. Okay, right? So this is the electronic configuration of krypton. This is the electronic configuration of krypton. Okay, so we can write it krypton 5s1. Clear? Krypton 5s1. This is the electronic configuration of rubidium. Clear? Next, cesium. Next হচ্ছে cesium. Okay, so cesium atomic number is 55. Okay, so cesium 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, next 4d10, 5s2, 5p6, 6s1. Okay, so this is the electronic configuration of xenon. Okay, so it will be xenon 6s1. Clear? Xenon 6s1. This is the electronic configuration of cesium. Clear? Finally, francium atomic number 87. So francium, so 87, 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 5s2, 5p6, 5d10, next after 5d10, 6s2, 6s2, next 6p6, okay, next 7s1, 7s1, okay. So this is the electronic configuration of radon, okay. So helium, neon, argon, xenon, radon, krypton, okay. Xenon, helium, neon, argon, krypton, xenon, radon. So this is the electronic configuration of radon. Clear? Rn 7s1. Okay. So general electronic configuration is noble gas configuration. After that NS1. Clear? Okay. Next come to another property, that is atomic radii and ionic radii. Second point is atomic radii and ionic radii. Okay. So same trend, atomic radii and ionic radii both have same trend. Okay. Again we take this table. Okay. So from going downwards, what happened? The atomic radii as well as ionic radii increases. Okay. So from top to bottom, both these increases. Okay. So we can write which one has largest atomic and ionic radii, that is francium. So francium greater than cesium, greater than rubidium, greater than potassium, greater than sodium, then lithium, and then hydrogen. Okay. So in general, atomic radii and ionic radii of alkali metals are larger, okay, in general, okay, and their atomic radii and atomic radii varies. How they varies? Okay. So its atomic radii varies. Atomic radii varies from 152 picometer to 265 picometer. Okay, so from this lithium to cesium. Okay, from lithium to cesium, this atomic radii varies in the range 152 picometer. 1 picometer means 10 to the power minus 12 meter. Okay, pico means 10 to the power minus 12. Okay, so 152 picometer to 265 picometer, the atomic radii of lithium to cesium varies. Clear? So atomic radii increases when goes downwards. Okay, atomic radii increases when go downwards. Next point, come to the third point, that is ionization enthalpy. Ionization enthalpy. Now, as the atomic radii of alkali metals are higher than the other elements, its ionization energy will be lower. Okay, so in general, ionization energy of alkali metals, okay, that is lithium to cesium mainly, we discussing lithium to cesium, are generally lower. Okay, ionization energy generally okay, low. Ionization energy generally low. Okay, due to higher atomic radii. Clear? And on the other hand, if we see the electronic configuration, that is noble gas, electronic configuration, and NS1. So if one electron remove from the system, it attains noble gas electronic configuration, that is very, very stable. That's why its ionization energy of alkali metals are generally low. Okay, what is ionization energy? Ionization energy means the energy needed to remove one electron from the system to make it a ion in gaseous state. Okay, now in previous discussion we know that when goes downwards, atomic radii increases, and as atomic radii increases, ionization enthalpy decreases. Okay, so from top to bottom, ionization energy decreases. Okay, so from top to bottom, ionization energy decreases. So highest ionization energy in case of lithium, then gradually it decreases. So ionization energy will be like that. Clear? Okay, so this is ionization energy trends of alkali metals. Next point, melting and boiling point. Next point, melting and boiling point. So in general, melting point and boiling point of alkali metals in general is low. In general, it is low. Yeah, okay. So they can easily melt. They can easily melt by application of low amount of heat. Okay. Next point. Density. In general, these metals are light metals. Okay, so their density is low. They are soft metals. Next point, electropositive and metallic character. So these metals are electropositive metals. These metals are electropositive. Okay, so that's why if these metals represent as M, so they can easily release electrons. They can easily release electrons. Okay. Next, oxidation state. Okay, so oxidation states of all alkali metals from lithium to cesium. Okay, we discussed lithium to cesium, that all alkali metals are +1. Okay, are +1, oxidation state +1. Okay, so yes, lithium to cesium, mainly discussing, we are concentrate lithium to cesium. Okay, their properties are widely studied. Okay, lithium to cesium, so they exhibit oxidation state of +1. So all the metals are unipositive, form unipositive ions. Okay, so lithium forms lithium plus, sodium forms sodium plus, potassium plus, rubidium plus, and cesium plus. Clear? Okay. Next, photoelectric effect. Photoelectric effect. Now what is photoelectric effect? When light falls on this metal, so they release electrons. Okay, they release electron. This is called photoelectric effect. Why they show photoelectric effect? This is due to having very low ionization energy. Okay, due to very low ionization energy of alkali metals, when radiation strikes on this metal, so electron will come. Okay, they produce due to low ionization energy. Okay, next, lattice enthalpy. What is lattice enthalpy? Lattice enthalpy is the energy needed to bind the cations and anions in an ionic compounds. Okay, suppose one alkali metal sodium forms sodium chloride. Okay, this is an ionic compound, so sodium plus is cation and Cl minus is anion. They bind together by a energy which is called lattice energy, which is called lattice energy. Okay. In general, lattice energy of alkali metals are very high. Very high. Okay. In general, lattice energy of alkali metals compounds are in general very high. Okay. Now lattice energy depends on the size of the ions. Okay. As the size of the ions increases, lattice energy decreases. Okay. As the size of the ions increases, lattice energy decreases because there is a more separation between the ions. Okay. So if I consider compounds, okay, that is salts of same anion of these alkali metals, suppose lithium chloride, sodium chloride, potassium chloride, rubidium chloride and cesium chloride, then which compound has highest lattice energy? LiCl, because size of Li plus is smallest, okay, lowest. Okay, that's why its lattice energy will be highest among these compounds. What is lattice energy? What is lattice energy? The energy needed to hold the cation and anion together. Okay. Now as the separation between the cations and anions increases, okay, so the interaction will be weaker, then lattice energy will be lower. Okay, so less energy is required to break the compound, that is separate the compound, because they are previously separated by a large distance. In case of ions, alkali metal ions of higher sizes like cesium or rubidium. Okay, clear? Okay, so next class we shall discuss chemical properties of alkali metals. Okay, so my dear students, please subscribe the channel and also like and share the channel. Thank you for watching.